Hello and welcome back to another episode of Learning Rust with Git Oxide. Welcome back, Sid, as well.
Hello, glad to be here once again.
And very nice background too, nice sun. It's already dark here, so I definitely envy you. That said, let's continue with a bunch of non-optional topics, which is all about options. It's not optional because it's really so, it's everywhere in the Rust ecosystem that knowing how to deal with booleans and options is super important. I think that's a nice segue to say, okay, it's nice that we have all these little thingies here, but how do you use them in practice? A bit more practical, nothing fancy. So if you have a vector here, with a bunch of things that can't be copied, what's the stuff that, this can be copied, right? So, does it matter whether it can be copied or not? It doesn't. Let's just use this. I just like non-copyable things because then we might get into borrow or ownership issues more easily, which is probably a reason to eventually swap that over. Okay, does that even
Always
work?
a good learning opportunity.
Yes. Let's just try to break stuff. So we have a vector v with a single thing, but what is it? It's interesting, huh? Because I was expecting this to actually fail compiling, but it doesn't. Because the 0 here, this could be u32, u something something. What is it?
Yeah, I'm not sure actually. Is there a default value that it just picks? Like
Yeah.
a default number value?
Must be.
Or type?
Must be. Let's find out what, like, how can we find out what the type is here?
I don't know.
What about guessing the type? So we know it's a vector, and I guess it's a u32.
Well, but then you tell it to be a U32, right?
All
That's not
right.
a real way to finding out
That's right.
the actual one.
That's right. But maybe you're wrong. No, you're not. You're just right. Okay, another way. What about that? Okay. So it has unit type here. Look at this. It's like an empty tuple, right? Like, it's so nice, actually, that they use this syntax to say, yeah, it's nothing. So we use it kind of as nothing, instead of making up something that we don't ever want to see in programs again, like null or nil, right? Or void or something like that. So very neat. But not much of information here. Huh? Still just an integer. And I think there is a default value because we can now calculate, we can make computations with that. So eventually the integer has to be something so that we know what the limits are. And I think it's documented somewhere, but I don't know what it is, and it doesn't tell you. And if you would try to assign that to something, we would always cast it in a way. I mean, not cast it, but we would define the value. And the moment we mention it, we change it. It's like this Heisenbergsche Unschärfe-Relation. Huh? You can't have both.
Exactly.
So yeah. Okay.
But isn't there I mean, I know I use a plugin in VS Code where it actually shows you the inferred type. I don't know if that works for you in IntelliJ as well, but I think maybe that's something how you can actually look at it.
I'm feeling dissed right now. Of course that works in IntelliJ. Yeah, but I disabled that. I don't know where to enable it. But let's see, maybe next time, because it was so noisy then, you know?
Yeah, it does get a lot noisier, but for learning it's great.
Let's just say to the audience, maybe if you know, leave us a comment below. Now, let's get some options business here. So what if I want to do this? I just want to access something that is definitely there. Huh? Does that work? Works. No crash, no issue. What about this? Okay. Index out of bounds. Makes sense. It's not there.
Makes sense.
So didn't Rust say it's always kind of safe and nothing bad ever happens? And I mean, this is very innocent, right? Like, oh, I just accessed something. And usually, but it panics. So usually in Rust, it's so explicit if something can panic. But here it's kind of implicit, isn't it? Is that still Rust? Yeah. There are places in Rust where it can panic by default. But there's always an alternative, which instead returns an option or result, let's say. If there can be errors, by the way, I think you can't bypass that. You always have to go through the error and handle it. However, here, there is no error that says, I mean, it doesn't make sense to have an error. Index not found. Please try again later. It's either there or it's not there, and that's it. So we don't have to over-engineer this. And usually when there are these common things that people do all the time, then you have these panicking functions that just make your code more readable because you don't have to go through all that clutter anymore. And people are also very used to having that, right? People, programmers, are very used to having that. So this is why it's there. And it's also safe because it's no problem to panic. Panicking is not unsafe. It's not uncool. It's just, let's say if this is a server, it's reducing your availability, right? So if somebody can make your program panic, then they have, in a way, successfully hacked you, but that's where it goes. They can bring you down. And then you're being restarted and, you know, they adjust your availability. So it's nothing super crazy, but also not nice. So there are, of course, ways to not do that. By the way, same thing goes for kernel development, right? So if allocation can fail, but this tells you it cannot fail, look, there's no result here. There's no something that tells you this could possibly fail, right? It's just working. I can change the size of the vector. But in fact, there might not be enough memory to do that because that vector will have to grow, probably. And that's a problem for kernels and for moon rockets or Mars rockets because they can't just crash if they're out of memory. They have to handle that gracefully and do something. I mean, maybe there are other ways. Certainly there are other ways to handle that too, but let's say it would be nice to not have your OS do that. On an OS level, you don't want that ever. And this is why they're usually non-panicking versions of this. So there's a bunch of alternative APIs that you can use. I think for that whole allocation problem, there are other ways to do that. Try reserve would be one thing that has an error if it couldn't reserve it because of out of memory, for example. So if you want to push safely, you could try reserve one additional one and then you can push, right?
So you're saying then that these are only used in very special or rare cases. So
yes.
Usually you wouldn't have to do this because it's fine if it panics.
Yes.
Yeah.
Exactly. I mean, look at this. This is a new API. It's unstable. I can't even use it. So it's really for this stuff is for the Rust kernel. Sorry, for Rust in the kernel. But that's the thing. Every operating system just gives you 64-bit of memory, no matter how much physical memory there actually is. And at some point you're being killed for being too greedy, but it will take you a long, long time. And that's just how it is. Programs there allow themselves to be killed, and programmers try to just adjust the size of the working set to make it fit into memory, right? This is how this works, and this is how we operate, and this makes it much more easy to write stuff like this and just say there's unlimited memory. And that's our assumption here. I just want to point out it's already assumptions, and everything can fail, basically. So let's have a failable API for something as typical as this. What about get? Yeah, I mean, let's just print this to get a bit of an idea. Let's debug, print it. Okay. And here is some 0. Let's make this a bit more obvious. Okay. And now something that isn't there. And we have none. Nothing panics. We can just deal with it. And say, well, unwrap or, we did that last time. Unwrap or some alternative. Yeah, we're getting somewhere. It still didn't tell us what the integer is, but it says get does not actually give us an owned version of it. It just gives us a borrow of it.
Mm-hmm.
Even though this is copy, right? Get always just gives you a borrow. So in order to make the unwrap or work, I have to make the type work. So I have to borrow this one too. And now it's fine.
And there's a special function to get it mutably or to get it owned.
Oh, let's go with the first question first. Let's get it mutably.
Yeah.
Yeah, that's interesting here. So now say I have a static number 422 and I want it to be a mutable borrow. I want a mutable borrow to it. Even though that is kind of, it looks so static, right? This is statically known in compile time and I want to change it nonetheless. Does that work? It does work because, I mean, Rust is probably smart enough to just allocate that thing on the stack and then I can just change it there. It's not a static variable. It's just something that is local here. And now for the second part of the question, or can it be owned? Huh. Do you want to answer your own question?
Well, I don't know how to. I'm guessing it can somehow, but I'm not sure how.
Okay, cool. So your stance is not your stance, your disposition is yes. It can be owned. Good. Okay, so let's have our vector here, right? So this is the memory of the vector and I just put it into my allocation. And now if I want to own it, let's also maybe put a string there. String from hello so that it's actually an owned thing. Let's go back to this. Okay, this should still work. And now what would have to happen to own it? Because owning means transfer, right? So now this thing is stuck in the vector. And now I want to, in the next step, want to take it out of the vector and put it into, and put it into a variable z. I don't know how to write that, maybe like this. Take it out and put it there, something like that. That's our transformation here. And yes, you're right. Sure, you can do it. Sure, you can do that. You can take it out and put it in, but that's exactly what you have to do. You have to take it out. You can't just get something out. You have to take it out. And fun fact, like if you create an option of something, let's create a new string here as non-movable thing, you can take something out of an option too, which then requires mutability and it will return an option. So that's still an option, but the original option doesn't have the thing anymore. So what we just what we just did is we have some string and then we take it and that string is none but some other option that comes out of take. Yeah, but it's about memory here. So the memory of that option is now empty, whereas some other memory now has an optional string in there if there was something. And that's...
Yeah, so the option doesn't go out of scope. You don't destroy it. It's just you're taking the value out of it and putting it somewhere else.
Okay. Yes, and that can be super useful if you literally want to rip something out of a structure without partially moving the field, right? So you want to keep it alive. And for that, you must make a detachable. And that detachable thing means an option. Like it's either there or not, so to say. And this, it's interesting to think about it in terms of detachable, because then, yeah, ripping out limbs is not pleasant. So let's just build the thing differently. Yeah, it's a robot, of course. So we're not talking about humans here ever. So then let's take it out. Let's take that thing out and put it somewhere else. We can do that. Let's go back here just to print something nice. So hello. And now one way of taking stuff out is to pop it off the end of the array, the vector. And now let's print again. Now get 0 is other, so we didn't get the original thing. If you would stop doing these shenanigans, it would be more clear. So it's now none. We literally popped, we popped x off the end. So
and pop also returns an option then. So if it's empty, it returns none. So it's safe basically.
Yeah, good point. I wasn't thinking about that at all. Yes. Because this vector could be empty. What happens? Panic? No. Fortunately not. It returns an option. See? And this is also how, like, look at that. Yeah, this is interesting. Yeah, it's just interesting to think about it like this. But I think no other language, you know, other languages like C or C++, maybe C++ is a better example here, or maybe even Java or whatever, or JavaScript, same thing. For the most part, they just give you a borrow to these things. They also don't take it out, right? They just have references all the time. They borrow it mutably even. Everything is mutably borrowed. And that's terrible. And it's good that it's not copied, but also not good because in a way copies are much safer, because then, yeah, you stay true to the two basic rules of every sane program, which I will not repeat here. So, okay, so this is options in practice, and most often what I do is sometimes you wanna manipulate something that is in this vector. You wanna filter it in particular ways, and sometimes you find yourself doing exactly that because you want to own these things as you adjust them. How can we modify something that is in the vector? Probably it has nothing to do with options, but maybe it does. So let's safely modify that. Let's have a function that says fn change, and we have some value that is an option. Yeah, what should it be? It should be mutable, right? So I just sketched this now. I want to have this function change v in place. Okay. And my first take is just give it the thing, but then it's not in place, right? Then I have to transfer ownership, and then it dies in here unless I transfer it out again. So we have to work with the borrow here somehow. And it should be safe, so it can never fail, because it's either there or it's not there. Just to bring in the option a little more. And the reason I'm saying this is, where do I put the mut? Like if I need a mutable borrow, where do I put it? Now I have two places where I could put it. Just say one, whatever feels most natural to you, and we will try that.
Somehow I feel it should be inside, because that's the thing you're trying to change in the end, right?
Yes. Yes, totally agreed. And it's a great rule of thumb. Like, never you want to borrow an option. Like, I don't know when that happens. There probably is rare cases where you only have borrowed options for some reason. There might be cases where some APIs return that. Maybe, but I don't think I encountered that. So once you see this, probably something is wrong. You always want to borrow the internal thing, the same thing contained inside of the option. Cool. So we know that this get0 is hello. And now let's modify it and change it. We can just say v get 0, right? And it's unhappy because...
Well, it needs an option. Oh no, it's getting an option.
It's getting an option.
It's not mutable, right?
Not mutable, right. So get mut instead. And that's also terminology we'll always see. Get mut, like this underscore mut. It's everywhere. So you just look for that and you know you're probably going to get something mutable then. All right, so that works. If I would run that, it would probably just run into this to do. And let's remember that to do, just put it there. If you don't know what to do, just sketch the structure of the program and put to do into the branches where you don't know what to do. And it will come together neatly that way. And we can do branch by branch, maybe have a test, maybe have a way to test it. And that's very, very nice to work with. I do this all the time. So now I want to change this into... hello. No, it's already hello. Into changed. So how can I do this? Can I say... It doesn't like that.
Yeah, so v is the option, right? And the option is not mutable, so you can't directly overwrite that. So what I think you want is you want to unpack.
Okay.
Yeah, I think, yeah.
You're right. The option is owned, right? The option is moving in here, and inside is a borrow, a mutable borrow, and that's all. So if I really want to overwrite this option, I actually can. I just have to make this mutable. I own it, after all. I can do what I want with the option. I can take it. I can take things out of it. But that only affects my option. That borrow is still available to the one who borrowed it. I can't change that. I can't just take it away. It's borrowed for good. And also this, like, I want to assign it to something else that is I need a mutable borrow here. This is what it's saying.
Yeah.
And I could just make it work. Like, what about this? And now the lifetime is not right, because that string is local to the function and has to live as long as this lives, right? Let's call this lifetime of this reference 1. So lifetime 1, because it's the first reference. The more references you have, the more lifetimes you have, because each has their own lifetime. And this temporary value here is freed at the end of this statement. But the assignment has to last as long as 1. As long as this string lives. So I can't possibly, as long as this borrowed string lives. I can't do that.
Because that refers to the outer scope, essentially. Yes. That's coming in. Yeah, that makes sense.
It's impossible, right? The cool thing is, in other programming languages, it's totally not impossible. You can just do that, no problem. Even though it makes no sense. No compiler will tell you, hey, by the way. Maybe some do, because they have simple checking of that kind, but very simple. or needs special flags to turn on these additional warnings. It's tough. Okay, so that's not the way. You said destructure it, huh? So match it. So some value. And look how I'm happily shadowing the existing. And I don't make up new stuff all the time.
Still have to get used to that.
So I have to do something here, and here I don't have to do anything. And as return, yeah, there's no return value, so I just do nothing. Okay, that seems fair, and now I have to figure this one out. So now here I have a borrowed something there. So now I should be able to assign it maybe, like v equals string from changed. Okay, still not. Expected mud string found string. Consider dereferencing here to assign to the mutable borrowed piece of memory. Assign to the mutable borrowed piece of memory. Okay.
Okay. So you dereference it to get access to the actual value, to the referenced value.
Yes, because that's just a handle to that memory, and I can treat it as a handle. I can do things with the handle, but most of the time you want to do things with the thing behind the handle that the thing points to, the memory. And that memory is mutable.
So without the dereferencing, you would have overwritten the pointer essentially?
Yes.
Yeah.
And you can do that. It's okay. You can say, okay, I would like to have my own local mutable string here and do something with that, but you know, it has no effect because it doesn't actually get out of that function anymore. But that does something now. Okay. And we see that now after the change, if I get this value, I change it in place. And that's one way of changing something that is inside of a vector. Huh? Just get a mutable borrow to it, and then you do what you want to do. But you can't ever take it out. You can't steal it from the vector. Let's get back to that. Okay, now that we learn about options, let's also, like whenever you see this kind of stuff, then we should probably be a bit better than that. Because it's clumsy, it's very, you know, this unused branch, it's 4 lines of code for one little effect, and it's common. You will do that a lot if you would do that. So whenever you write something that common, you can always expect to have a nice little function on option for you, waiting for you. Okay, so first of all, let's see if we can have somebody help us with this. Let's edit configurations, create a new one. My favorite tool. Oof. Clippy. Command is Clippy. You have it with your installation, so nothing to be done here. Apply. And let's see if Clippy has some useful hints. Ooh, cool. What?
That's checking the files.
It's checking the other thing, checking the whole. But here, this one. You seem to be trying to use match for destructuring a single pattern. Consider if let. Okay, so that's already an improvement. And look, you can just copy paste this here. Ta-da!
Nice.
Okay, we went from 4 lines to 3 lines. It is an improvement. Thank you, Clippy. Appreciate it. Let's keep running this. Okay. Works. Can this be better? We basically say if there's something in the option, apply some effect to that something. Let's see what we have. It's map. Okay, and now I can just copy this in here. And now we just went from, see this semicolon here? Because map returns something. It returns an option with the changed result, or with whatever comes out of here. But and this is now the return value of the function, because
yeah, no semicolon.
Yeah, so you see the default return value is unit. So we don't write that out, we don't spell that out, but it's there.
Mm-hmm.
And because I created an assignment here, this means assignments are also expressions, right? And expressions have return values. It didn't force me to put a semicolon here to say, oh, this can't be an expression. Yes, it's an expression, it's fine.
Mm-hmm.
Which is something I wasn't so very aware of, by the way. I think it's the first time I do this. And this is why we see this error. Interesting. And what comes out is, okay, an optional unit, because the outcome of this expression is unit. And to prevent the automatic return, we have to put a semicolon, and that should work just fine as before. And it does.
Okay, so map takes the value in an option, unwraps it, and then gives it to you in the closure.
I wouldn't use the term unwrap, because unwrap means you consume the option forcefully, take out its value and make it available to you outside of the option. And if there's nothing, it panics.
Okay,
and this
so
will not panic
inside the option.
Yes, it peeks inside the option. It says, if it's there, I call you. Literally like that. Hey, I'll check. And if I have something, I'll call you and give it to you. But as a, yeah, what is this now, right? What's the type of this thing? Because we can actually answer this question. So what do you think is the type of V now? We already know.
Yeah, I would say that it's the mutable reference contained value, or the contained type.
Okay. I will write this here for you, like you said. And let's see if that works. And it does. It's exactly that type. Let's see how that's implemented. Look at this. What does this tell us about this option here? So self is the option. But what does this tell us?
That it's owned, you mean?
Yeah. And if ownership is visible or present in self, this is when we call methods consuming. Because the method can only be called once. Because after the call, look, I move self into the function, right? In the end, it's just a function. And I move self there, and then it's gone. Poof. But out comes a new option. And this is why you can match on self. You can move X out of self if it's there. And then you move it into the function f. And the result of that is moved into a new option. Because otherwise you couldn't do that.
Yeah.
Look at this. Let's really quickly do that just to hammer this home. It's interesting, I think. My option, we have some t and none. And then I input this option for all t's. My option t. The faster you want to type, the more time you waste not typing the right thing. Okay, now we have a different version of the map, the non-consuming one. So I say I take a borrow of self, maybe even a mutable borrow because I want to allow the function to adjust the value. Okay, so now we have the function f, that is an implementation of any function that I call once. I mean, we go a bit too far here. Let's just take it as it is. But yes, we have to differentiate between that and choose the right thing. Let's talk about that in another session. And that fn once, what does it get? It doesn't get t because we don't have a t. At best, we have a mutable t. And what does it return? It returns some value u, which is dependent on any call of the function map. And then we return an option u like this. And now the implementation would look very similar. We match on self, it's mutable. We have some value here, and we return some, whatever this returns. Otherwise, we return none. And, oh yeah, right. It's my option, sum, and not the one from the standard library. But here we do return an option from the standard library, so that's very confusing. But it should serve the purpose of hammering this home because you see it compiles. And look what happens if I do this, which is what the actual map does. Where is it? Here. Hey. Sorry. I pressed something there. See, so this is what the actual map does. Hey. And I'm not allowed to do that here. Because all I have is a mutable reference to t. I can't take it out. However, if you have, I mean, that's the cool thing. Once you have a mutable, once you can write your memory, think about your memory as the possible states that you have. Like my memory can represent none or some. So it should be possible to move something out of me while replacing me with something else that is valid. So either another t that I make up or none. So I should be able to produce this by just having a mutable self. And in fact, you can. And this is something just to remember. And we'll look at that, how that actually works in a moment. I just don't want to implement more of this. Or maybe I should. Maybe I should allow me to take something out of myself. Okay. So that we can implement this. So how this would look like is self take. And that should take a mutable borrow of me as well, but return something that I can destructure that I own. So I want to have an owned version of myself. So let's do that. Do some magic. So I have to take myself as mutable, otherwise I couldn't call this. And there's nothing else because I know my new value will be none. And I return a my option that is owned. Note, not myself or borrow to myself, but something very new that has t inside. The t which was formerly inside of myself. Okay. So with this declaration, that should already compile. Oh, look at that. Because sure, once I own this thing, I can destructure it like before, right? No problem. Let's call it net take, because otherwise it would just be too confusing. Or take map, something like that. So it would be a take map that we manufacture here an abomination, I think, but it's for learning purposes, so I think it's all right. Then, how do we implement it? And by the way, you see to do there, like how I don't go ahead and try to do something that I might fail at and have a lot of compile errors. First, I see if the signature makes sense for the thing above. If the answer is yes, then I continue. And that's something to remember when writing Rust. Tiny steps compile, tiny steps compile. Or in this case, cargo check, because cargo check is faster than compilation. This also produces bytecode that you can run. But if you want faster builds, just to see if it works, use cargo check, right? This is really important because compile times can be high because LLVM is quite slow, which produces the executable code. All right, back to this implementation. Now, the gist of it. I have something mutable of myself. I want to take out what's there and replace myself with none. And it's related to memory. I want to write to memory kind of more directly. I want to swap my memory out. A swap, mem-swap. Really useful operation. And only then, just with mem-swap, this can even work. And there's std mem take or replace. So take I can call if I myself have a default value, which I don't. Or if you know what you want to replace yourself with, use this replace. So what do I use? Myself as a destination. This is the memory to write. It takes a mutable borrow, which is exactly what I am here. And as a source, it takes an owned option. And I want to replace myself with none. And you see what happens here. This is already working. It's compiling too. Because now I take whatever is in me out, I own it now instead of being borrowed, and put something else in its place onto my own memory location. And the thing that I took out, I can return. And then you can do with it whatever you want. And that's exactly what take is. This is how that is implemented. And that's a thing, something super useful to remember, that these things exist, for one, and that you can use it too, second. And it will come in handy in these times when your borrow check will really not work and you can't, yeah, that's that.
Yeah, it does feel a little bit like cheating because yeah, it's like kind of a back way around this whole system, right? Where you kind of explicitly say, okay, I know this will work, and you will just swap it out to something owned. I guess it can be very useful, yeah, but it does feel a bit like cheating.
True. I mean, think about it like this. This mem replace is just another form of, let's see how if you can see how it's implemented. Yes, we can. This is read what's there, keep it, write the new thing, return the result. So let temp be my current value, write another value to my own location and return temp. This is how a swap is implemented. It's just a swap. But it says it's unsafe. Because why is it unsafe to do a swap like you would do in any other programming language? In C, C++, have a pointer, do that, fine.
Well, that's exactly the point of the borrow checker, right? To make sure that there's nothing unexpected happening to the data, that you're thinking it's there.
I think what I want to hear is that somebody now is able to read from the destination address, but also write to it. Kind of, I mean, it's two different steps, and that's exactly, we have a reader and a writer at the same time. That's exactly what the borrow checker won't allow you to do, but is exactly what you need here. Also, this reads, I mean, this literally it's a byte read, right? It's reading the bytes from that memory location, putting them somewhere else on the stack. Let's say hypothetically, this is all optimized, right? So this doesn't really happen, this data movement, but let's just say we have this here, and then we read the bytes, just a byte clone, put them here, and now we have the same thing twice, literally. And then we read the source value that is also moved here. So that doesn't, so that lives here now. And we take it and put it here. Boom. We overwrite that memory location, thus forgetting that this clone existed for a while. Like for a while, there were two copies of the same thing. And think about it, this is totally violating ownership. There can't be two copies of the same thing, because that's a move, but it's not really a move when you do pointer read. This is why these reads are unsafe. And then a moment later, I overwrite it, right? So that clone didn't exist for too long, thank God. And then this copy here, this clone, so to say, which looks very, very similar to the original. It is the original, byte by byte, after all. But we know it has just been transported, right? It's if you have been transported using a teleporter in Star Trek, are you still the same? Yes and no. And then it's moved out again. So these bytes, they move. But you know how it is when bytes move, they're actually just copied elsewhere and forgotten on another point, right? It's just like blip, 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 blip. And only one ever exists at a time, but sometimes two exist at a time. That's why it's unsafe. But fortunately, this unsafety is abstracted, and they claim that this is safe. If you read from destination but directly write the source into it afterwards, such that old value is not duplicated. The duplication I just talked about. It's happening, but it doesn't persist. Nothing is dropped and nothing here can panic. So whenever you do this unsafe stuff, you have to ask, will code run like drop code, right? We implement drop for something, and then as it gets dropped and stops to live, some code is executed. So would that code be executed twice, for example, on the same memory location or different memory locations? Answer should be no. Panics. If I do something, can this trigger a panic somehow? And then there is some weird stuff with my state for that moment? Also no. Not here anyway. This is why it's always safe. But this is always the questions you have to ask when you do that. And if you forget, then under circumstances, stuff can break and cause issues similar to what you know from C and C++.
But again, it forces you to be very explicit, and using this keyword then it really makes you think about, is this really safe?
Yes. So here we are in safe land, but just one jump away, we are in unsafe land. And we don't want to be there ever. And back to your remark, it's strange that you can work around the system like that. Well, you don't work around it. That's the point. A mem-swap is a mem-swap, even though technically it's not. But semantically it is, and you can't bypass that atomicity of the swap. You can't. It's going to happen. And nothing can stop that from happening. This is what this text tried to say. Drop, panic. It's not going to stop. It can't stop. It continues. And that's what you want. So it's safe. And it's something you do and you can do, but you don't usually look at these abstraction levels, one level up. You usually have an option and you take stuff from it. And under the hood it does that. So when you feel the need to replace something yourself, you can probably do that. Sometimes it's the right thing to do, but maybe you really want an option.
Mm-hmm.
Or something like it, anyway. Okay. We have 50 minutes in. This is a long session, and look at the 5 lines of code that we've actually produced here. But I think now we understand how the whole mutation works, how interaction with options work, and learned a little more again about ownership in the process, and a lot about generics if you really want to go into that. But it's actually pretty simple here. I mean, it's understandable, I think. not too much to see there, actually. I think this is a good time to close the session. Is there anything that is on your mind? It looks like it.
No, I'm just trying to take it all in, really.
Okay.
Once again, it's been a lot, it's been dense. But yeah, I agree. It was very informative, and I did learn a lot about options.
Yeah, it's for me, every time it's so interesting for me because I learned so much too. I mean, it's like now you have to phrase it and say, look there, look there, look there. And in a way that shows that you've truly understood it, at least from my point of view. And maybe somebody who has written the Rust compiler will dig down 2 more levels and show you, look, this is how pointer read is implemented. I'm like, whoa, no way. It's another universe again. How many levels deep can you go? Well, today it's just 3. All right. Thanks a lot, everybody, for watching. And thank you, Sid, for being here. I'll see you all next time.
See you soon.